All right, this is going to set you up to do one more of these finding all trig functions, but this is going to involve tan, which requires a little bit of a uh, slightly different process here. Um, let's take a look at SB page 173, which I have up on the screen. You'll kind of want to keep this handy as you're working through um, these 5.2 problems. Pretty much everything you have been asked to know is on here other than the unit circle values. And here's what I want to point out to you. In the fundamental identities here, if you notice, this here is a form of your x squared plus y squared equals 1. Of course, here we have the y. Sine squared is y squared plus x squared is equal to 1. So if we have this identity that sine is equal to y, well, then we can just substitute this in, okay? So it does turn out, these are called Pythagorean identities because they're all derived from the Pythagorean theorem. There are two more of these that we use that actually you can memorize them or you could actually derive them. This is kind of a cool little thing that not a lot of people have necessarily noticed where this comes from. What if I was to divide my sine by a cosine? Okay. If you notice, if I divide sine squared t by a cosine, I'm going to get tan. So what I'm going to do is I'm going to divide everything by cosine squared t. As long as I divide every term by the same thing, I'm still in balance. Okay, what I want you to notice is this gives me tan. Okay, sine squared theta or sine squared t over cosine squared t will give me tan squared t. Anything over anything will give me the 1, right? And notice the reciprocal of cosine squared t will be secant squared t. So this turns out to be a second identity, okay, that will become very helpful if we're given a tan, all right? So that's where this comes from. And I'm going to share over the whiteboard here, and we're going to do one of these that involve a tan. Okay, so here is an example where we're given the tan of a t, and we're told that this is in quadrant 3, okay? Also notice that this is not a unit circle value, and in fact, it's not even a Pythagorean triple, so we're not going to have any little shortcut tricks. If I were to say that it's y over x, right? That tan is y over x. I'm going to know these are both negative because I'm in quad 3. They had to tell me that. But what I don't know is I don't know what the ratio, I just know the top part of the ratio, not the bottom. So I have two possibilities here, okay? Again, kind of going back to the way I did it before. I can do this algebraically, or I could use SOHCAHTOA, all right? I'm going to show the algebra. If you're going to do algebra, you do have to use this Pythagorean identity, okay? Where I just did this a second ago here, that if I plug this in, and I'm going to actually go ahead and put this as a 1 over the cosine squared of t, that's the secant, okay? So what I would do is I'm going to now substitute it. If I put this in and square it, I'm going to get 1/16. Well, of course, that's going to be plus 16. 16ths are going to equal 1 over my cosine squared of theta. I could actually have solved this as secant squared and then taken the reciprocal when I was all done. But notice I'm going to get is equal to 17/16, okay? And if I flip this upside down, I'm going to get my cosine squared of t, in this case, is going to equal 16 over 17. And if I take the square root, I'm going to get 4 over root 17. And then I have to rationalize that. Technically, I get 4 root 17 over 17. Go back to my original, right? This is the tan of t. That is the opposite over the adjacent. And notice that for tan, that's the opposite is going to be the y over the x. What this does is this gives me the missing root 17 is what I had here. What this tells me, for example, is that my tan it had to equal 1 over root 17 over 4 over root 17. And then if I rationalize it, I get these. So I'm going to end up with root 17 over 17 for my y and so on. This is a fair amount of algebra involved with doing these. Some people like doing it. I'm going to show you the other way that I actually prefer, and that's going back to simple right triangle trigonometry that you would normally have learned in a geometry class. I've drawn a little right triangle here where you can actually see that the ratio of the opposite side of theta, right, if we go opposite to the adjacent, okay, is 1 over 4, all right? The reason I've sketched it this way is if you notice, if this is in quad 3, then kind of what we're saying is, it's kind of like we have a little line. This is, I would call this my tan of 1/4. If I understand slopes, this is about a 1 to 4 slope, right? And what I've done is I've drawn the triangle as it might fit inside my unit circle, right? That this would be my x distance and this would be my y. They should be a 1 to 4 ratio, but they're not going to be 1 to 4 because remember, on the unit circle, the radius is just 1. So x has to be less than 1, okay? But we're just going to use what we know about SOHCAHTOA and right triangles to find out what is this other component. What would the radius be if I had gone out of the unit circle? And here I'm just going to use the Pythagorean theorem, right? This is going to be the square root of 1 squared plus 4 squared, which is going to be 16. It's going to be the square root of 17. Notice now I have all my sine, cosine, and tangents now based on a right triangle, based on SOHCAHTOA. It's really quite easy. Now, if I'm remembering, right, I can't have a negative distance, but if I'm on the unit circle here, right, this is in the negative territory here, okay? So my cosine of t is going to be negative 4 over the square root of 17, and of course I need to rationalize that, right? Okay. My sine is going to equal negative 1 over the square root of 17, which then becomes negative root 17 over 17. And notice, if I did put sine over cosine, I would get positive 1/4. So that checks. The tan was already given to me. That's my 1/4. Okay. And then I'm just going to take the reciprocals, and these are the nice ones to look at for my reciprocals. My secant, right? I'm actually kind of going in the opposite order. Whatever I started with, I'm going to go with. So I had started with cosine this time. So secant would be the square root of 17 over 4, keeping the sign. It's still going to be negative. The cosecant of t is going to be negative root 17, right? It's going to be the reciprocal of negative 1 over root 17. And then finally, the cotan is going to equal positive 4, the reciprocal of 1/4. So I do find it a little easier using SOHCAHTOA when I'm working with tan. But those of you who really love algebra, you can use substitution with the tan squared plus 1 is equal to secant squared, which will then give you the cosine and go from there. All right, that's 2 ways to go about that.